Okay, so the time has started. So welcome to my session on AI features in Oracle 23 AI. My name is Andrzej Nowicki, and I'm a part of the database team here at CERN. So here is the obligatory contact information and my LinkedIn contact. So if you want to reach out to me after the presentation, feel free to do so. I'm just going to briefly introduce the IT department of CERN. It's almost 400 people that are responsible for providing services for all of other departments at CERN. So we are providing the infrastructure both for experiments as well as other teams that are not necessarily related to the experiments. A little bit about the databases at CERN. So Oracle has been the database solution from the 1982. So quite a lot of time has passed since it was selected. We have more than 100 Oracle databases with more than 11,000 Oracle accounts, and the environment is quite complex. And as well, we are providing the database on demand service, which is roughly 600 MySQL instances and 400 Postgres instances. And the total size of our database environment is more than 5 petabytes of data. So if you have any questions about that, feel free to ask, but at the end, or maybe at the coffee that follows the event. But this was just to warm you up a little bit. So Oracle 23 AI. This is a major release for Oracle because they have been preparing a lot of new features that will help with the AI workloads, with the machine learning. So if we want to use it, it hasn't been released to the public yet for, let's say, the on-premise solutions, but it's mainly available in the cloud right now. So you can use livesql.oracle.com, which gives you a possibility to run your SQL statements, to give it a try. You can spin up an autonomous database with some limitations. It's not yet available in all of the regions, but you can spin it up just to play around a little bit with it. So this is what I'll be using for my presentation. So I spin up an autonomous database in the cloud, and I'll use it in my demos. And there are other possibilities. What is probably the most interesting is the possibility to have the Oracle Database 23 AI free, which is available as a Docker image, as a VirtualBox VM, or an RPM for many flavors of Linux. And also there is an ARM version that was released last November. So this is something that you can use on your machine to develop, to have some kind of proof of concept. Just to get to know the product a little bit better. So the first part of my presentation will cover the Select AI. So Select AI feature is the possibility to query your data using natural language. So for example, we can ask the database what are the total sales of Tom Hanks movies, and we get a result which should be based on the data within our database. And here we can see an example that underneath we can run Select AI Show SQL, which will show us what was the SQL statement used to provide the answer from the first part of the query. So we can see that the AI model is capable of running a query that would join with a different table. But this is something that's only available in the cloud for now. So forget what I said about Docker, about the RPMs that you can install. This is only available in the cloud for now, but that's going to change probably in the future. But let's see how that works. So we have our user that writes a question to our engine. And this is a question like any natural language question. You can use an IDE, you can use a web app, you can use text. And this will be fed into the Oracle database, the autonomous database. So what the database is doing, it's taking this natural language question and it arguments it with the metadata about your schema of the objects that it's allowed to use, because you need to specify exactly which objects am I allowed to use for the Select AI feature. The data compiled like that is then fed into the LLM, and the LLM produces a SQL query, and the SQL query will be run against your data, and the result will be sent to the user, And as an optional steps, the fifth step, you can also make it into more like a conversational model where your previous queries, your previous questions will be retained and you will have like a conversation-like interaction. And then you get the response, you get an answer. So it all looks quite well, quite impressive on the marketing material. So let's see how to set it up. So the first thing that you need to set up is the credentials. The credentials are needed to access the cloud resources. In our case, I will be using the OCI generative AI service. So you need to provide the credentials for the OCI. I've blurred it out here. You need to provide a private key. You need to provide the user ID. The OCI ID is an, let's say, identifier that's specific tied to your user and the tenancy, so Oracle will know which data you are allowed to access. And then you need to create a profile. So we will use a provider of OCI. We use the credentials that were created in the previous step. We use a compartment. The compartment is needed just so in the internal billing you will be able to see that your queries were run as a part of which, let's say, project. You, of course, need to set up a region so that your query lands in the correct region. And then you provide the object list. So, for example, let's do a very simple profile where we pass only one table, the table employees, from the schema admin. And this object data, so the full contents of the table will not be shared with the LLM. Only the metadata about this object will be shared with the LLM. So column definitions, comments, maybe some information about private keys, unique constraints, etc., but not the actual data in the table will be shared. And we have this example table with some 3 entries just to start with something. So we need to set up the profile, and we can also ask the LLM the questions directly, which are, let's say, independent from the data that we have in our database. So we can use the Select AI chat to ask the LLM a question directly, like you would, for example, going to ChatGPT website. So we can query how many people we have in Poland, live in Poland, and it's not something that we would have in our database, but it's using the information that's already in the LLM. And we can also, in the next line, we can ask it how many employees do we have, and then we can use the show SQL to see how many employees do we have, like what was the SQL used to return this information. What we can also do, we can do the narrate, and the narrate will change how our output is phrased. So we will get let's say, a statement. So this will be like a real conversation instead of getting, for example, a tabular result. We will get a sentence that will tell us, oh, we have 3 employees. So it's time for demo. So I hope that everything works. So what we start with, as I said, we will create the credentials just for visibility. Like I've cleared out this path, we will be using something else underneath, but this is what we would do. We would need to set up to, from the very beginning, to use the Select AI feature. Then we create the profile. So we have the same situation as on the slide, where we just share the employees table. So if I ask the Select AI query without enabling the profile that I have just created, it will say that this is not a proper SQL statement, because it's not. We need to enable the profile, so we need to just set the profile to the OCI that was created previously, and then we can use the direct, let's say, chat. So this will be the direct command that would go directly to the LLM. As you can see, this is hallucinating a bit because it's estimating that the Vox days at CERN, it's roughly 1,200 attendees, which is, I don't think is the case. I haven't seen that many people here. But let's see how it goes with our data. So let's see again, we have the table employees, where we have 3 example employees, and we can query the data. We can query with the Select AI how many employees do we have. We get a result. And as I previously presented, we can use the show SQL, which will show us the query that was run underneath. We can also use the narrate, which will give us the the response as a sentence. And then we can ask for example, something else like which employee earns the most, and we get the employee name that earns the most. But let's try something a little bit more complicated. So in order to have more complicated queries, I need more data. So I will be using an HR schema, which is let's say one of the default schemas that are provided by Oracle with some sample data. So this is already in my database, and you can see that I'm sharing all of the contents of the schema HR to the LLM. And this is the structure of the schema. So you can see that it's a little bit more complicated, which will give us some ideas on what we could query. So, for example, if we wanted to see, just as a, let's say, a little exercise for you, just think for a second, how would you query which regions do we have locations in or departments in? It's a rather complex query where we would have to join several tables. So we will see in a second if the AI is capable of doing that. But let's see. Again, a little bit, let's learn our data set a little bit more. So how many employees do we have? We have 107 employees. Let's check the show SQL. So you can see that I previously asked the question about how many employees do we have, and it was, just because my profile was different, it was accessing different objects. It was accessing objects in the admin schema. Now I'm asking the same query, but it's accessing the HR employees. So data that will be queried is different depending on the profile that I'm using. So if I ask our query, our LLM, which employee earns the most, this is a bit tricky. It takes a lot of time, surprisingly. And actually, this is phrased in a way that the LLM didn't know how to respond. So we get a response that, unfortunately, the select statement couldn't be generated from my prompt and using my data, but it, let's say, reverted back to the LLM knowledge, so it gave me some general idea which, let's say, which employees are earning the most, which jobs have the highest salaries. But this is not necessarily what we wanted to achieve, so let's try rephrasing our query, and we can rephrase it that we list the 10 highest paid employees, and now it's understood by the AI, so we get a list of our employee data. Let's have another tricky question. Which female employees earn more than average? We get a result, we just assume that it's okay, we got some query, it's probably okay. Can you notice what's wrong with this result? I would say line number 3, Alberto, doesn't seem like a female. So let's see what happened. We have the HR employees table, and I don't see any gender field here. So we don't have a column for that. So what actually happened? Let's do the show SQL. And here is the query that was run, and we can see that the model just assumed that the first name would finish in an A, E, I, or O of U. And the LLM just assumed that this would be the case, and we of course know that it's a hallucination. It's completely wrong. But by giving us this query, if we for example, didn't look properly, if we didn't notice it wasn't something evident like Alberto, we wouldn't know that there is a problem. So you always need to double check the results that you get from a tool like that, because it's completely unpredictable. Okay, again, I played around a little bit just to find the corner cases, the things that worked, that didn't work for the AI. So imagine that we want to list the biggest and the smallest department. And probably 90% of the people in the room assumed that by biggest and smallest department, I mean the people that, the number of people that work in this department. So by querying which are the smallest and biggest departments, we get some result. This is not the name of the department, this is the ID of the department. Let's see what was the query that was run underneath. Well, actually it was running select min on the department ID and max on department ID, so it actually resulted in a result set with the department with the smallest department ID and the department with the highest department ID, which is not necessarily what we wanted to achieve. So let's try to tweak our prompt a little bit. So let's rephrase it in a different way. So let's phrase it in a way that's which department has the most employees and which the least. And we get a list of departments along with the number of employees, which is something closer to what I wanted to have, but let's just assume that I wanted to get only the biggest and only the smallest departments, but including the ties. So I would want to get the shipping, just because it's the department with the highest number of employees, and then the public relations, HR, and administration as the ones that only have one employee. So it's not a very complex SQL statement, but let's see if we can make the LLM phrase it for us. So we can, again, check the SQL, which will show that we are running it from employees and we are joining it to the department, and then we are grouping it by the department name. So far, so good. Let's try to rephrase it a little bit. We still get the same result. The query that's run underneath is still the same. But I've run this presentation, the same prompt in October last year, and this is the result that I got from the same query, which was which department has the most number of employees and which the least. I got exactly what I wanted, and it's a different query than what I get, what I keep on getting right now. So let's try being a little bit more specific. So let's try a query which is which department has the most number of employees and which the least. Show me the biggest and smallest, include the ones that are tied. It didn't understand what I wanted to have. So I'm thinking, okay, maybe I should just use some punctuation marks. Same thing if I make it a little bit more readable. So while playing with that, I made a typo by mistake here. And this made my query work. So this is what I actually wanted to achieve from the very beginning. So it's very tricky to get the prompt to actually get whatever you want to achieve as a result. So you should be always very careful if you're using that feature. But what we can do, again, we can use the show SQL to see what SQL was generated. And we can see that we have quite a long query that was using the join from employees and the department, and then it's just returning having count, where is the maximum number of employees. So something that we would write ourselves maybe. And this is the same query with the same prompt, and it's a screenshot from a recording from the conference in October, where we got the same result with a different query, and that time it was written in a way that was, let's say, easily readable for human eyes. It was way easier to understand. So let's try again something even more tricky. So how would we check which regions are we in? Let's say that it's a database of a company that has their departments in different locations across the world. So which regions are we in? So we query it like that. It turns out we are in 5 different regions. Okay. So let's check in which regions do we have departments. Well, this query failed. It gave me no result. So how is it possible that we have we are available in 5 regions, and we do not have any departments in any of the regions? Well, this was a little bit too complicated of a query. So if we start going smaller, we ask it which countries are we in. We get a list of the countries that we in, and then we can ask which locations are we in, and we get a list of the locations. But it's still, we can, by looking at it, we can just assume that we cannot be in 25 different countries by having only 23 locations. So again, we are in some kind of a state where the results are not what we would want to get. But let's skip it for now. I will explain later what happens here. So let's see what else is possible with the querying. We can modify the result set, so we can force it to provide us the country names and skip, for example, the state of the location. We can return departments with their locations, so we can play around with the form of how the data is returned. We can add also the manager names. So we can join multiple different tables. Maybe it's helpful if we gave the model some hints on where to look for the data. We can also do where clauses. I mean, we know that these would be where clauses, but we can also phrase them like include only the departments that are in Europe, and we will get a list of places, the departments that are based in Europe. And then we can use a show SQL to see what was the query that was run underneath. So we can see that the query got quite complex by just phrasing stuff differently. We can see that it's a query from the departments, which is joining employees, locations, countries, and regions table. So it is quite complex. So it is possible to phrase queries, to phrase prompts that could be useful for us to generate SQL statements. But you need to always double check of the result. So let's go back to the query of how many countries do we have departments in. So a very simple, very naive result is 27 countries. And we try to ask the AI which country has the most. But then the AI is lost because by the default configuration is that each query, each prompt that we do is a separate query. So we are not keeping any type of context along the separate queries. So what we need to do, we need to enable a conversation parameter. So we can set up the conversation to true, and this will mean that up to 10 previous prompts will be transferred along with our prompt for, let's say, context, to contextualize our query a little bit. So let's select how many countries do we have departments in. We have 27 countries, so still some result. And now we are asking which country has the most. And this is a very interesting query because it works half of the time. Sometimes you get a result which is satisfactory and you get a list of the countries. Sometimes you get a result that it's the AI is lost, it doesn't know, the context is not good enough. But for now, it failed. We can do some more queries, like, do we have any locations in Switzerland? And then we get a count that we have 2 locations in Switzerland. We can ask the AI to list them, and then it lists something completely else. So it still doesn't know what to list, so it lists the departments. But right now, if we rerun the query that failed just 3 queries ago, which regions do we have departments in? Now it's giving us the correct answer. So I know the data, I tested it myself. There are only departments defined in 2 regions, in Europe and Americas. The other ones are just regions, the definitions of the regions, but there are no departments in them. So actually, by keeping this context, by setting through the conversational parameter, we impact the result that we get from the LLM, and it sometimes improves our results. So we can check the query that was run underneath. So we can see that it was a query from countries, where we inner join on regions, locations, and departments. And you can see here on the graph that it's regions, countries, locations, and departments. So this is actually how we would write a query. But of course, writing it by hand would mean that I would have to check the names of the tables, the name of the columns, etc., the foreign keys, etc. So maybe it could be useful in the future if your data is properly documented. Maybe that can be facilitated to improve the speed of writing SQL statements. But what I also found super interesting is the explain SQL feature, which will give us the same SQL that was run a second ago, but it will explain what are the step-by-step steps needed to get our result. So we can see that we start by selecting the regions table, then we join the countries, the locations, and the departments, and as a result of this query, we can determine which regions actually have departments and not just naively which regions do we have defined in our database. We can also provide a SQL statement and ask the AI to explain it. So, of course, you could do the same thing with the LLM, but this has the additional benefit of LLM will be fed information about your schema, so it would know what are the names of the columns, etc. If you send the same query to the LLM, if you, I don't know, ask ChatGPT to explain what does this query do, it will just assume based on whatever is covered in this SQL. But imagine that, for example, you have some column names that are not understandable to the human eye, let's say, but there is some information in the comments of the tables, in the comments of the columns. The LLM, by using that, the LLM would also have this information because this would be put as context to your prompt. So that's the finished part of the Select AI. So this is some more slides. So I'm just showing what went wrong in some of the queries, some of the attempts that I took before. So for example, one of the cases was the AI tried to join the departments with regions table, and we can see that there are some tables in between, so you cannot directly join regions and departments. So what it tried to do, it tried to join location ID with region ID. But by looking at the schema, we know that this will not work. And we have another example of how it tried to do it. So trying to join regions with manager ID, which is completely wrong, which is definitely not the way to do it. But it gives us, the feature itself, it gives us some flexibility. It's very future-proof because we can define different profiles for different users, different use cases. We can use different models. So for example, we can compare Cohere, Command R with Llama from Meta. So there is a plethora of providers that are supported for this feature, and there are multiple models that are supported. So probably this feature will improve, it will grow in the future, and I'm looking forward to see that it becomes something that can be reliably usable. And again, the true parameter, the dimension of the conversation parameter, which helps a little bit. So up to 10 previous prompts can be included in your prompt. And here is an example of how sometimes, this is also a log when I played with it a little bit with the querying model, that sometimes giving it some hints, even if not directly, will help you get the result that you want to have. But again, I will put more pressure on it. You always have to double check the SQL that's being run underneath, because it could be simply wrong. So what about the costs? It took me roughly several hours playing with the Select AI feature over 2 evenings last week. And the total cost of running hundreds, easily, if not thousands, of the queries with the Select AI, the total cost was, I don't know if you can see that, but it was $1.86. So it's not super expensive, but it's also not the cheapest. I think it could be useful for quite big schemas or something where you need to have a lot of previous information to understand the schema and how the schema is configured. Okay, so let's move to the second part of my presentation. I see that I'm running short on time. So the second part of my presentation is building a beer recommendation system, and how we can do it, how we can achieve it with the AI features in Oracle. So the first thing that we need to know are vectors. So vectors in artificial intelligence in AI is a ordered list of numbers, of scalars, that can represent the point in a multidimensional space. And the n number is the dimensionality of our vector. So the vectors itself are known in math. They need to have some meaning to them. So we need embeddings. So embeddings are vectors that have been created by some embedding model. So for example, a bird's nest and a lion den are similar to each other, while day and night are opposite. And the embeddings will convert the real-world objects, or text, or image, or videos, into mathematical representations that we could use in our system. And then we need to have a model, and models are typically designed to take some form of input to into output, give us some vectors, so we will use the vectors then to run the similarity. So how can we put it all together? Let's say that we have some input, like a movie, a picture, some piece of text. We have the embedding model, and then we have the embedding, also known as vector, that we can put in our database. So for example, let's assume that we have a beer system where we have some descriptions on the taste of the beer, and then we push it through the embedding model in order to get a vector. And that's just a warning that it's a simplification. Normally you would cut the text into chunks if, in case you have texts of different length, etc. But this is just a simplification for the purposes of this talk. So let's vectorize our input data set, and then we just assume that the similar input, so similar descriptions of our beers, should result in a similar values of the vectors, of the embeddings. We can calculate the distance between the vectors to find similarities, and our recommendation system will be solely based on the fact that we are looking for beers that are similar to something that, for example, our user liked. So how can we calculate the similarity? So this is just an example of a two-dimensional vector. So we have x and y axes. Let's just assume that these are sweetness and legs. So we have dogs that have legs and are a little bit less sweet than cats, and then we can calculate the cosine distance between the two. So we just create a line from the start of our axes to the dog, to the cat, and then we can calculate the cosine of the angle alpha. And for example, bananas don't have legs, but they are a little bit more sweet than the animals. So we put it somewhere in our space, in the vector space. We draw a line again. We calculate the cosine distance, so we know that the beta angle is bigger than the alpha angle. So we can just say, quite using this information, that a dog is more similar to a cat than it is similar to a banana, which sounds trivial, but if you have lots of information in multidimensional spaces, it's not so easy. So essentially the same thing will happen in the similarity search, but for our model that I'm using in this presentation, we have 384 dimensions. So the calculations will be a little bit more complicated, but the idea stays the same. And there is, before we go into the demo, let's say, I just need to mention that there are some limitations on the similarity, because it's not the similarity that we think about it logically. So for example, healthy and unhealthy will be quite similar together, even though for us it seems like it's completely the opposite. And healthy and not healthy will be even more similar. And this is because the embedding model will assume that, oh, they are similar in a way, because healthy and unhealthy as words, they are both adjectives and they are both related to health status, so they are quite similar. So for example, dog and a banana, it will be less similar. And we can also put phrases. So I like beer will probably not be very similar to a sentence that table partitioning is an amazing feature of relational databases. And it's true, it's not very similar. I like beer versus I like indexes in databases, it will be a little bit more similar. But for example, I like to index my data and I like indexes, this will be also quite similar. So there are some limitations, but just to simplify it for the needs of this presentation, let's keep it as it is. And just like as a mental experiment, let's just think what is the opposite of whatever word that we can think of. So for example, what would be the opposite of king? It could be queen, it could be prince, it could be a poor man, it could be a banana. You never know. So it all depends. So there is you cannot actually, life and world in general is way more multidimensional than just one dimension. Okay, so enough theory. So with 23 AI, we can keep everything in Oracle database. So we can keep the text, we can keep the embedding model, and we can keep the vectors. So let's have a data set. So I found a data set on Kaggle, which has more than 3,000 beers along with their descriptions. So we can see, as an example, like 3 beers, or 4 beers, with some information about their taste, some material from marketing brochure about the beer. So this is our starting point. We can add a column to our table, which will be of a new data type vector, and then we will have the vector table with CLOB value. So the most popular way for people to do embedding is Python, but of course this is a Java related conference, so we are not going to do it like that. But this is a result that we would have from Python. We can put it in the embedding model. We can put it also inside the database. We define it as a function that takes, let's say, data as input. We can also do it in the cloud, so we can access our embedding using a PL/SQL feature vector embedding. So you can see that using this model that I have imported into my database on the previous slide, I can embed this piece of text as data, and I can put it in our database. So the vectoring of the data that I have in my table is as simple as one simple update statement. So we update our table beers by filling in the vector information using the vector embedding, using the info column where we kept the description of the beer. We could also do it from the Python script or some other client by calculating it outside of the database. So I made a short summary, as a short summary. Using it in the cloud, like the embedding took 73 seconds. By embedding it on my MacBook with a single-threaded Python code, it took 43 seconds. With 4 threads of the Python code, it was 20 seconds. So there are some potential possibilities to improve, let's say, by parallelizing. And also, I'm not a big Python programmer, so I used ChatGPT, and it worked quite well out of the box. So optionally, we can create an index on the vectors, but let's skip that. It's not that important. So how we would search our data, we can query our data based on the vector distance. So remember this comparison dog versus cat. We calculate the distance, the cosine distance. So we can do it twofold. One way would be to calculate the vector value outside from let's say, a Python script or an application. And then the other option is to actually use the model that we have in the database. So we could use a prompt in the database. So for example, if we query for lemon, we would get some beers which would have some kind of mention of lemon in their description. So for example, we can see that there is a beer which is called Sundrift, which mentions citrus and lemon zest. So far, it's quite basic, but as like the distance of the results is bigger, we can see that, for example, we were looking for lemons, but this one doesn't mention lemon at all. It just mentions citrus. So we have some semantic information in the query that, lemons are part of citruses, so this could be something of potential interest to somebody that was looking for similar beers. And we see that there are some that mention lemongrass or citrusy notes. So this is how it would work like. So let's enjoy the beer. So let's have a quick demo of how we could query. So I have the query that I presented in the presentation. So we will be using the embedding inside the database, and the parameter that I will put in here, this will be what will be our starting point. So let's try. I have some suggestions here that I've tried, and they worked. So let's try first with a query that was herbal but fruity. So we can see, and apologies for the new lines because that's SQL+. So if you're not used to SQL+, then it could be not very readable. But we were asking for something that was herbal but fruity. So for example, we see that we have plum-like fruitiness. Another beer offers us some ginger, spice, orange, and toasted grain. So we have some options. Let's see, for example, I was playing a little bit with the queries. So by querying for cigarettes, we got some smoked stouts. The embedding model knew that cigarettes are close and similar to smoke. So this was the closest thing that it could find. So let's. I'm a big skier. That's why my contusion is in place. So I tried skiing. So for example, we have a Snowdonia ale, which mentions mountains. This one is a ski resort, a ski arena area. So it knows some kind of stuff. So another one that I have on my list is SQL. I personally like this one because the SQL is similar to a DBA, right? So our model knew that SQL, DBA, database administrators, this is something that's close by. So I don't know if we have any suggestions in the room what I should look for. CERN? Oh, I didn't check that. Okay, I think it's just gibberish. We are not that good on creating beer. So yeah, there was a question about a Polish proposal, Żywe. So the model that we are using is only English specific. So there are models that are multi-language, so they would work with other languages. But if we started to do something that was in a different language, it would not necessarily work. But I checked, I think, Honey, and then. No, it's not here. But I remember playing a little bit with the different languages. I was checking, and I found something that there was, maybe it was French. No, but okay. Let's move on. Okay, so I have 3 minutes left. I'm gonna if you want to have some prompts that you want to test, feel free to find me. We can have some fun. But I just want to summarize very quickly what are the real life usages of a system like that. Because of course it's just very basic with the beer recommendation system. It's just a very simplified process, but what are the actual real-life usages? So imagine that we have some text, and this is actually like the first few phrases from Romeo and Juliet. So what we normally would do, we would slice up the text into chunks. So we would put it into smaller chunks. Let's just say for Romeo and Juliet, we could use the line breaks. So we would put it into separate lines, and we would vectorize each line. So we would get some vectors. So this pair of chunk and a vector we would store in our database. So we would create let's say a knowledge table for our system. So we have some knowledge, and then let's just assume that we have a user that's asking our system about some details about houses. So we would vectorize, using the same embedding model, we would vectorize the query from the user, and then we would try to look for similar information in our database. So we would run a similarity search, the same case that I did with the beer, but with something a little bit more serious. The database would result with some information, with some relevant information. So for example, let's just assume that the closest out of the 4 rows that we had here would be the line about the 2 households, both alike in dignity. So you would feed that information along with the user prompt to an LLM, and we would create a result out of that for our user. So we could tell him that, for example, both houses had people of equal status. So this is something that we could use, and for the real-life scenarios, we would interrupt it here at that part, just to make sure that the information that we are feeding into the LLM is relevant. So, for example, the querying the vector information from the database, it's not a very expensive operation. So what we could do, we could list as much as, 50 entries. We could re-rank them, see how relevant they are to the query, try to use a different model maybe, and try to sort the relevance to the original query, and then we select only the ones that are the best quality and feed it into the LLM, and then the LLM would provide us with an answer to the user, and that's how you get the retrieval augmented generation. So by using all of features that it's nothing quite serious, nothing complex, we are creating actually a system that the systems like that are becoming more and more popular. Okay, so this was my last slide. Here are some references of the materials that I have used, and of course the beer data set, the Romeo and Juliet from Shakespeare. Remember to visit the Science Gateway, and thank you so much for your attention. If you are interested in seeing the slides, here is the QR code to the website where I put on the slides already. Thank you. And I have 5 seconds if somebody has questions.
If I have a case where I need to vectorize specific keys of a JSON object, what would you say is the technique to do that?
So let's just assume that you have a JSON object and you want to vectorize just one key of that object, right?
Just say it's a bunch of nested stuff, and I want one specific nesting that I want to use to vectorize so that it can be used to search the whole object, right? So say there is an object called credential, right? On it there is a signature and there is claims. I want to vectorize the claims because I want the claim name to pop up in my search, which will find me the object, right?
So what you would do, like in the case that I presented, like I mentioned briefly the chunking. So instead of the chunking, I would say that you would need to modify your JSON object just to get out the key that you are interested. So as you said, like claims, for example, you get the text that's in the claims field, and this is what you put into the vector. So for example, if you already had the JSON in the database, you could use a different 20 Oracle feature that would extract just this information from this one, let's say, key. And then you would, instead of feeding the, where was that? So here, instead of using info, because info, it was a column, it was a simple column in my table. Instead of using info, you would have JSON query or something like that, which lets you use JPath, I think, to access this key. So this way, you could do it all in your database. Okay, thank you all so much.